So hopefully that'll contrast with everything else. Okay, without further ado, I'd like to introduce Gerry Bond, who's very kindly put to come tonight from Reading Astronomy, or Astronomical Society. Thank you, Gerry.
Okay. Thank you for the welcome, everybody. Can you hear me okay? I won't insult your intelligence by putting up the URL for the Reading Astronomical Society. If you Google any two of those words, we probably come top of the list. So all those questions about when can we join and how much it costs, etc., 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 I don't need to answer them. You're all geeks, you can do it yourself. Okay. For the sake of this talk, I really need darkness. But for your sake, expecting this to happen, I did a negative of that picture. But this is the last time you get that favour, so we may have to have the lights out in a moment or two. By the way, I'll just interject here. The talk is advertised as about imaging, amateur imaging for night sky objects. I have two friends who are into this. I am not. Your lucky night is that I don't know much about what I'm talking about. Because if I let Peter Ticknell or Alan Halsey loose, giving you a talk about what they do for imaging, you probably wouldn't understand a word. Well, we're going to base a lot of tonight on this area of the sky, which is in the east-southeast currently in the evening, and we're all pretty much familiar with the constellation Orion, Taurus, and some wonderful objects that are in this region. And in fact, a nice part of the Milky Way rises up in this direction. It's about 7 o'clock in the evening. Bear in mind, I want all you to be very pragmatic and practical about when you go out to observe the night sky, because there is a famous anecdote of an astronomer, professional astronomer, who rang up an observatory to get some observations of some deep sky object, and the assistant at the observatory said, "What constellation's it in?" And he said, "I'm an astronomer, not a Boy Scout." Does not anybody see the funny side of that? That's illuminating in itself. Right, so here we go. We're going to tell you very quickly about the geography of what some of the objects you're going to see in a moment are. In this sword of Orion, hanging down from Orion's belt, there's a nice M42 nebula. There's also, I think I've got images of the Barnard 33, the Horsehead Nebula, which is just around about these bottom edge of these three stars. Bear in mind that we come to the shortest day of the year. The most sociable time to do astronomy is about an hour after sunset. And from the 21st of December onwards, an hour after sunset gets later and later and later. And the stars are going by 4 minutes earlier each night. So the combination of those two times, if you observe an hour after sunset, means that this wonderful bit of the sky we don't see very much of, because by March it's raced across and disappears into the lightning evening sky. So make the most of it now. I have an object in Cygnus to show you later on, and Cygnus is a summer constellation, and summer constellations seem to hang around an hour after sunset for months, because in the autumn the hour after sunset is getting later and later, is improving for us all the time. Right, first of these fantastic objects, which you all know, when you look at it you probably call them the Seven Sisters, or that fuzzy patch there. To the naked eye there's 6 or 7 very, very bright stars, extremely interesting object. It's about only 100 million years old. And this rather old picture, probably taken in the 1920s or 30s, by this 36-inch reflecting telescope at the Lick Observatory in California, is quite famous because it is surrounded by this nebulosity. Part of the talk tonight is to impress upon you that amateurs in lower early can get images as good as this professional telescope from about 70, 80, or even only 40 or 50 years ago. This reflection stuff was believed to be the remnants of the gas and dust cloud that collapsed to form these new stars. But in 100 million years, even that is a very short time in astronomical terms, they would have blown this material away if it was from which they have formed. So we will go straight on and show you an image of Peter Tickner in darkest lower early, and I'll give you some. You can start the questions in a moment if you like. It says here, can we get a bit more darkness? Because I'm not sure whether you can see these striations at the back. Does it get better? Can you turn them off? You can see these striations in this material. Let's cut to the quick a little bit. Here's a professional picture of the Pleiades. Right. This material is blue. When spectroscopy became all the rage, if I can use that sort of expression, in the late 19th century, it became the tool for finding out what things are made of in the universe. And the spectroscope says that this dust is the same spectrographic quality, is exactly the same as the light from each of the stars. So what we're actually looking at is a reflected light. The far side of these stars, because all pictures that you see in your coffee table books are three-dimensional, bear in mind that you just see a flat surface. We cannot tell which of these stars are further away and which are nearer. We all know that they're in the same cluster and lie at roughly the right distance, which in this case I think is about 400 light years. But they are passing through or in front of a cloud of, if you like, black dust. Silicate material, but it's solid material, it's not gas. Gases, as you know, transmit light. It would shine through the gas material, but in this material, whatever it is dust. Very little gas, because if there was gas around these extremely bright stars, and I'll jump a little bit to something in another part when we talk about M42 and the Trapezium Nebula. If there is gas in the vicinity of these bright stars, you bear in mind that at this age, the stars are radiating about 80% of their light in ultraviolet. So even though they're 400 light years away, we can see them easily with the naked eye. Their total bolometric output, that's all the spectrum, is in fact very great indeed. Okay, so let's look here. This is the professional image. An 8-inch telescope achieved 80 minutes luminance, 45 minutes of red, green and blue, total image time of 2 hours and 5 minutes. What you might wonder what luminance is. Luminance basically is the frequency of your eyeballs with a few cutouts for infrared and ultraviolet, compressed a little bit, but it's used in imaging to increase the contrast. It is in fact the black and white background. If you're a television engineer, I think there is some sort of technical term for it, but it's the dynamic range is provided by the luminance factor. And in this image is actually then composed of red, green and blue, so that you've got the natural colour. And a lot of the imaging that we do is to compare red, green and blue. An amateur telescope would actually have a disc with 4 holes in it and a red, green and blue filter in 3 of the holes, so that you can take pictures in each of the different colours, and then the astronomer doesn't actually look at anything other than the computer screen when he starts mixing the colours to achieve this final image. When you look at colours in an astronomical picture, you have to bear in mind that, so I'll try and stand still for you. You have to bear in mind that the human eye is not going to be, the vision of the human eye is never going to be replicated at these levels of intensity. This is not a dark object by any means, we'll see some more in a moment. But the human eye at these levels of intensity is only going to see fuzzy grey. In fact, they do actually have real colour. And a lot of the questions I get asked is this a real colour? Well, you can forget it, because most of the amateur astronomers who compose some of the lovely images that you see have actually decided to use such things as, say, the Hubble palette. The Hubble palette is an entirely theoretical concept of if it's radiating ionised oxygen, we'll make it orange. If it's ionised something else, we'll make it blue. If it's ionised something else, we'll make it another colour. 3 colours mixed that have nothing to do with the natural colours of the ionisations of those elements. Right, let's go back. This is Peter's efforts from low early, and it's pretty good when you compare it with the book, the picture in Robert Burnham's book. And here he is. His technique for getting this picture, not by any means the most definitive version that Peter takes anyway, but it's just a nice one to show you. Luminance and red data only. He worried about the cloud. He's testing his EQ8 mount. We'll see one of those in a moment. Not using any auto-guiding. We'll talk about that in a moment. 5-minute subframes. So it's a camera with 130mm aperture. 130mm if my arithmetic is about 5.5 inches. APO, achromatic lensing. Now, this is a refracting lens, not a reflecting mirror, and the expense involved in making a large refracting lens which doesn't cause achromatic aberration is quite great. There was a man in the 19th century, in fact I think it was a century earlier than that, who got the theory of putting two different types of glass lenses together, one convex, which as you imagine is a circular pattern. If you integrate all the little bits of the lens, they all turn into little prisms, refracting the light to a focus, but light of different wavelengths refracts different amounts. So with an ordinary convex lens focusing your light, a single point of light, which a star is, will show you some rings of colour. Red is focused at a further distance than blue. The next leap of faith then was to put in a different refractive index glass in a concave lens and glue it to the convex lens. And that was then a reverse prism, which tended to bend the light back somewhat away from the converging focus, so it actually corrected the business of red being refracted least and blue refracted most in the convex lenses. The APO gets to be very expensive, and I won't bore you with the details because frankly I don't really know them. A third glass lens is glued to this complex item, which allows light to be transmitted through it with the least possible chromatic aberration. So there you go. That's the kind of expense that I'm going to put you to if you want to take up this hobby. How are we doing? Just for the hell of it, this is a Hubble telescope image of one of those dust clouds. And it really, really does look like a dust cloud. When you look at the images of deep sky objects in a coffee table book or on the internet, basically, if you think you're looking at a hole in space, if you think you're looking at a dark cloud, if you think you see a shock wave, you probably are. It's a very pragmatic and sensible way you can relate almost everything that's going on in these vast areas of space, and a gas cloud, collapsing cloud, can be hundreds of light years across and contain thousands of solar masses of material. But the physics that's going on there, you can replicate in your living room. We'll get to that in a moment as well. This is Peter Tickner's rig. We'll try and tell you what's going on. But under here there's a large amount of concrete. Keep this very steady. This steel pillar has to be rock steady, no vibration. a large counterweight because we're going to describe what's on here in a moment. But the drive is a clock arrangement, basically. This axis here tilts around so that this plane is parallel with the Earth's equator, and this axis is pointing at the North Pole. Peter says it's pointing at the pole star, but I'm sure it's not pointing at the pole star because the pole star is about 3/4 of a degree away from the real pole, and Peter's images are a lot better than that. So frankly, this is pointing at the North Pole, roughly. This plane is parallel with the equator. The Earth is rotating eastwards, so we're actually heading towards the sheds in the background of this image. Okay, and so as this clock rotates, the telescope and this counterweight will go this way around in 24 hours, and 24 hours of sidereal time are about 4 minutes less than 24 hours of the time on your wrist. And just to go through some of the little stuff at the top. Actually, I wonder whether... okay. I've been defeated by Microsoft. Under here, there's a lovely image of about 12 different astronomical CCD cameras that you can buy that do various jobs. You're not missing anything by not seeing that image. They vary in price from about £100 to about £10,000. So you take your pick. Peter's got another telescope here, linked to software. He calls it the guide scope. Now it's possible to arrange a telescope to view one particular bright star. The software tells you when it's locked on, and it will then guide the telescope. You're telling me now that I've just told you that the telescope will follow the sky anyway. Why the hell do you want to do the guiding? Well, it's not that accurate, and if you're going to leave this set up for 8 hours or so at night while you go to bed, taking an image, you really want it not to drift off slightly, as it surely will do, but the guide telescope and the software will keep tiny corrections going so that the image stays in the same place for hours at a time. Anything else up there I've forgotten? I can't really read it from here. Carbon fibre tube, no, that's all boring. Yeah, okay. Any questions at this stage? Yep.
Does the guide scope manage to keep tracking, or do you just assume there's no cloud cover at all during the whole process?
Yeah, that's pretty crucial, isn't it?
If you're relying on a guide scope, you can't keep tracking. If you're relying on...
As far as I know, Peter doesn't have any automatic weather detection. He's also someone who doesn't really go to bed till 4 o'clock in the morning most nights anyway. So yeah, but you can. I'll digress a little bit here. There's a guy called Guy Hurst who manages a thing called the Supernova Patrol from Basingstoke. He is quite famous in professional and amateur astronomer circles because he runs this network of people throughout the UK, and you know, the fingers of two hands will do you. We're not talking about thousands of people, but they will run their telescopes all night with a built-in program to image maybe 100 or 150 galaxies throughout the night. And the next morning his job is to get up, look at the images, compare them with previously taken images, and if there is a supernova in any of those images, he will quickly telephone professional astronomers who want to be on the case as soon as possible. And all over the world there are people, and most supernovas these days are actually found by amateurs doing just that. So your question is quite valid. If your cloud's over, you need to know so that there are means that you can... Basically, you want the roof of the observatory to shut, don't you? Because it might rain. Okay. So where are we going? This is another one of Peter's images, which I have chosen because it is an extremely faint image. This is the Western Veil Nebula. There is an Eastern Veil Nebula. You can't see the spot that I'm describing on the wall, on the floor, but the whole thing I think is about 3 full moons across in size. And this is a gaseous remnant of a supernova that blew up something in the region of 8,000 years ago. And astronomers now, professional astronomers, can see the expanding material, the rate of expansion, calculate back to when and where the explosion probably took place. This star has nothing to do with it. This is 52 Cygni, and this constellation, this material is in the constellation of Cygnus. As I say, Cygnus is with us through most of the summer and wasn't on the diagram that I showed you at the beginning. Here's the details. Narrow band image. So he's used H alpha, oxygen 3 and sulfur 2. Don't worry about that, but just merely register that this image has been taken in 3 quite specific light frequencies. I don't know those academics among you who only see light as photons and the other academics who only see light as waves. You have to be much more accommodating than that to be an astronomer, amateur or otherwise. But this has been taken in those 3 specific images, in its 3 specific wavelengths combined together to give you this reddish image. Now, it should be red because H alpha is the predominant light coming from this region. And the local stars of Cygnus, there's some quite bright ones, shining through rather large distances of space, are exciting this gas to actually emit radiation. I'm not quite sure what some of the terms are. I've heard it referred to as synchrotron radiation. What I do say to people who are probably not so academically inclined is that if you look at a fluorescent tube in your kitchen, you're looking at a rare gas with an electric field flowing through it, and it glows. That basically is the principle in a lot of emission nebula that we see in space. So I've already covered 2 important points about deep sky objects. The Pleiades are surrounded by dust, which glows when light shines on it, but it's a reflection of the light from the stars. And we're now seeing this light which glows through excited, ionized emission of light because it's being excited by the presence of adjacent bright stars. There's a third type we'll come through in a moment. The Attic 383L is one of those wonderful CCD cameras that you can now stick on telescopes. And he took it in mono with those filters. It's 130 millimeter. And 130 millimeters is a very small aperture for equipment which is doing images of this quality. Okay? Anybody with questions about aperture and so on? Because we might cover it in a moment. Yeah? Can't see anybody, so you know, if you can be standing on your head and waving your hands, feet in the air, I'd never notice. But so shout out if you've got a question. Okay, it's notable in a lot of the old textbooks that they say things like it's an extremely deep, dark, faint object. You'll be lucky to see it at all in a visual telescope. You know, the words notorious. Difficult to see. Observer can see the nebula clearly in the telescope with an oxygen filter. Maybe if you live in Arizona, certainly not around here probably. And almost all the light is in this ionized oxygen from this nebula. Okay, let's move on. Trying to think now what this is. Oh yeah, M81, Bode's Galaxy. This galaxy is in the constellation of Ursa Major, so it's never very far from the North Pole. I think you'll find it's combined with another one called M82 that is actually situated just off the screen up here. We may see an image of that in a moment. It's quite remote now. We're talking about 300 million light years. There's a pair of galaxies that are associated, and this is the image that an amateur in Lower Early has obtained, it's Peter again, 8-inch f5 Newtonian. It's the one that you saw on the picture, with an ATIC 383 camera, colour, H-alpha filter, and a reducer coma corrector. The quality of some of these images, when you try and use a sort of a wide field and get a faster focal length response, and I know what the technique, how to explain that an f4 lens is faster than f5 or f6 and so on. But the reducer coma corrector is, as I say, you go on the internet, you go to an astronomy dealer, and you buy something that's going to improve your imaging. Basically, it's giving you a slightly wider field, less magnification. It's effectively shortened the focal length. And the coma correction means that some of the stars around the edge of the picture are actually in the right place and form dots. When you see one of these pictures, the most dedicated, or the way you can tell that someone has really taken trouble about doing this, is that the dots of stars are actually tiny circles, not elongated or out of focus. But those of you who've read a textbook on astronomy will have read that stars are only ever seen as points of light. You cannot magnify them. That's true to an extent, but what you're getting with the practical use of even chemical film, as well as digital imaging, is the larger quantity of photons from a bright star actually hitting, spreading, and causing a larger dot on the plate that a dimmer star would cause. Difficult to explain, but quite important, because if you go back to the late 19th century, when photography had got to be developed and was coming to be quite a practical means of doing star catalogues, you could look at a photographic plate and determine the difference between one star's brightness and another star's brightness by the size of the spread of the photons on the image, the spillover. Are we talking about quantum effects here? So I don't really want to go any further than that. But in theory, stars are points of light. To reinforce what I've said, though, a lot of these things have diffraction spikes, which practically proves that they're points of light, because the diffraction spikes are due to the bits of metal inside the telescope light path, which are maybe crosses holding up various mirrors and items in the light path. And the refraction, or the diffraction of light waves passing these edges causes the diffraction spikes to appear. As far as I know, none of our members actually put one of those effective diffraction lenses in front of their image, their cameras, in order to make the picture look better. Sort of thing that you see on magazine images. This is a small input of professionally obtained photograph of Bode's Nebula, of Bode's galaxy, superimposed on Peter's picture. So you can see now why I was hoping to have a little bit more darkness. Okay, this is a combination. This is also Peter, taken from lower early, of Galaxy M81 and M82. And incidentally, we come to an astronomical feature that, as it's science, you need to prove everything that you see. There are all kinds of things that come to mind that what you see is not what you think. There is, for example, this is just one small example of this, not visible on this image, even if you had the lights out, there is a wispy filament of material that seems to come off this spiral arm and go up towards this galaxy here, which is M82, commonly known as the cigar galaxy. And it was thought, because of the proximity and the alignment, that M82 was dragging material away from M81 to some extent. Latest argument is that some of this material is just background dust and dirt in our own galaxy. Okay? In fact, you look at larger pictures of this, I haven't got any to show you, but the M82 galaxy itself has actually got a mass of red material which lies slap bang in front of the center of this disk of spiral material. It's probably a spiral, but not quite edge on to us, so it gives us this ellipsoid shape. But there is in professional photographs, professional images, a mass of red and black material lying in front of the core of the galaxy, and so there's a lot going on there. Interesting to study. And the equipment here is the Zatic 383 camera again, with the reducer, etc., etc. And this is in luminance red, green, blue, and enhanced by hydrogen alpha. When you go back to this image, can you see these little red spots around these spiral arms? Because each one of those is an intense region of collapsing gas and dust, and it shows up brightly as red. In fact, a lot of the galaxy is showing up bright, but it's showing up brightly as red because in the cores of those red spots, there are actually very new hot stars just appearing, and it's those hot stars that are locally lighting up these red dots. More of that in a moment. Alan Halsey, another good observer, actually lives in North Court Avenue, quite close to the campus. And as you know, that's not the most, not the least light polluted area of Reading. This 3 stars, this one looks like 1 star, this looks like 2 stars and a third, perhaps some others, with a little bit of nebulosity around it. And this, to the naked eye, looks like the 3rd star, the middle of the sword hanging down from Orion's belt. This material is all known collectively as M42, the Great Orion Nebula, although if you really know the textbooks, this little bit here is also called M43, and a lot of this other mess around has got various other catalogue names. If you see this dark material looking like a hole in space, because of the arrangement on this image, it actually looks to me like smoke in front of something burning, if you like. That's almost exactly what it is. Where you had the dust in the image of the Pleiades, which was behind the stars and illuminated by them, this stuff is dust which is in front of the stars and is blocking out the light coming from beyond. So we have the 3rd class of nebula, which is a dark nebula. Trying to think now, Barnard was this famous astronomer who made the catalogue of these objects. So they've all got Barnard numbers and Barnard names. Take a note of what Alan is using, not particularly a large telescope, again only 150 millimeters, about 6 inches, Newtonian, and he's using a 450D camera. That's a Canon camera modified by Hutech. Now, Alan is not married, doesn't have a lot of expense and responsibilities in his life, but we were horrified when he bought a brand new Canon camera, took it to bits and removed the infrared filter that Canon build into all their cameras so that you don't get disrupted images when you take them out to take pictures of the kids and the scenery and the mountains during the daytime. When you use a camera for tourist purposes, Canon do a lot to ensure that you get what your eye would see. Astronomers don't like that, and Alan, on his postman's salary, bought a brand new camera, Canon, and started taking bits out of it so it would get more light coming to the receptor of the sort of light that he wanted. And since then he's actually gone on to this company, I think they're in Arizona or somewhere, who will sell you a specifically modified Canon camera. They buy them from Canon, modify them, give them a guarantee, post them to you. They cost a bit more, of course. 6 subframes at 4 minutes stacked in Deep Sky Stacker, processed in Photoshop. Well, there's a lot of stuff going on in that sentence. When this hobby first grabs you, you find that you read something on the internet that you can use a webcam to take deep sky images. You use a webcam, you set up the webcam videoing a deep sky image, and you finish up with a video that may be half an hour or an hour long and 15,000 images. I feel the question's coming, maybe. Of that 15,000 images, what are you going to do with them? Well, some will be good, some will be very bad. But the programs like Deep Sky Stacker, which is just an ordinary software program that you will let loose on a folder of images on your computer, you tell it what to look for. For example, you choose a star as a reference object, and maybe another star, and the images will be registered one with another. The Deep Sky Stacker software knows what to look for in terms of, and this is more important with imaging planets, of course, because they're smaller and can wobble with atmospheric distortion more. But it knows what to look for in terms of image quality, focus, and what should we say? That an image doesn't look in focus; it compares them, one with another. But actually, you can tell it to take the top or the best 10% of images or the best 50%. There are parameters that you can change in the software, and you finish up. Well, in this case, Alan finished up with 6 subframes, all of 4 minutes, but stacked with Deep Sky Stacker. Right? I mentioned that about 15,000 images because this is the possibility that software does give you.
5 minutes, Gerry.
5? Okay, great. Getting back to the theory then, we've got 2 images that are probably taken by the Hubble Space Telescope of this star, and I refer to it as a star because that's what it looks like to the naked eye, in the center of this object here, which is these 4 stars, possibly 5 stars, and I say possibly because the right-hand image is taken in infrared, but this is visible light of probably the most interesting area of the sky accessible to northern hemisphere observers. It's actually very, very slightly in the southern hemisphere. It's just south of the equator, but never mind, we get to see it quite well. These 4 stars, now I said the Pleiades are spread out a little bit in the sky. They're only 100 million years old. These 4 stars are certainly less than 4 million years and possibly less than 1 million years old because they have just started shining. They've started to photonically, if you like, solar wind being what it is, and you can actually have light pressure pushing the dust and solid material and the gas away from the region that created them. So this is actually literally a hole in a gas dust cloud that's just been created by these stars that have just formed. Now in this image you can see more of them because this image is taken in infrared. And infrared, being a longer wavelength, is the sort of light that would just sail past tiny particles of light without being affected. To the non-academic people I talk to, I say, go to the beach and look at a pier standing in the sea. And if a sea with large waves comes crashing towards the beach, the legs of the pier don't make any difference to the size of the waves that arrive on the beach, because the legs of the pier are small compared with the length and amplitude of the waves. So long waves go sailing past small objects. That is why infrared light will penetrate to the centers of galaxies, which are covered and surrounded in actual dust, because the dust particles don't interfere with the longer wavelengths of infrared. So you can see more stars. Some of these stars here are actually embedded in bits of dust presumably behind these 4 that we can see with visible light, but they're embedded in bits of dust that make them invisible. But they very, very soon will be visible. They are blasting away that dust that's surrounding them right now. I'm probably not exaggerating to say there's some academic somewhere who's waiting for the first chance to see a new one of these stars appearing from within its dust cloud. Okay, we'll end there because this one's quite good. I don't know if you can actually see this, because this is something I took in the Shetland Islands in the 1980s using Ektachrome film, and it's about 15 seconds worth of the constellation of Orion. So it's a fixed camera, there are star trails, but it's Ektachrome film just exposed in an ordinary Canon A1 film camera, and that object, M42, in reality is actually crimson, according to chemical film, colour film. And that's because this stuff around it that's actually glowing, the emission nebula, is hydrogen gas glowing at, I think, 21 centimetres, the ionised hydrogen frequency, and it looks to our eyes as to be bright red. Don't expect it to be bright red if you just glance up at the sky without specialist equipment. But if you do expose the camera for a long period, you will see that these things do have colour. For instance, here is Betelgeuse, a surface temperature of about 3,000 degrees showing orange, and this one here is Rigel, surface temperature of about 20,000 degrees showing blue-white. So Max Planck was right. Okay, just drag me off whenever you want. I won't worry about these images. We'll go straight to this one. Just to inspire you a little bit, this is an 8-second image taken with an ordinary DSLR camera. There's the details. 8-second ISO 1600. And Mark Sharon, a friend of mine, who specialises in taking images that are not guided. Just sitting a camera on a tripod, pointing at the sky, take a picture. In 8 seconds, you will see that the stars do have very, very tiny trails. Even in 8 seconds, the sky moves quite considerably. But if you do this time after time after time after time for a period, around about now, the 13th of December is the peak of the Geminid meteors, which are debris remnants of a now defunct asteroid. You will occasionally see one. And if you're lucky enough to have the camera pointing in the right direction, and the 8 seconds that you have it exposed for, you actually see a meteor, you'll get a recording of the meteor trail. Thanks for listening. That's it. Okay.
Great. Thanks, Gerry.
Questions? Anywhere. Yeah, no, not necessarily up. Not even necessarily towards the radiant. Anywhere in the sky where there's Earth's atmosphere, and that's everywhere above the horizon, it is possible that a meteor, Geminid meteor, will pass through that bit of atmosphere that you're looking at. If you go out with a companion, for example, all face in different directions, if you're into actually counting them. But if you do that, then you're going to see one and the other 3 aren't. The other thing about meteors that's quite an interesting factoid is that they're like snowflakes on the windscreen of your car. They tend not to hit the back windscreen. Now that's a trite way of saying that if you wait till midnight, your observing position has moved over to the front side of the Earth, where you're more likely to collect meteors. Get the idea? Everyone's looking very puzzled. Have I said anything tonight that is... Most of you are academic, I would imagine, but have anybody raised a hand and said they've learned absolutely nothing? No? Okay. And there anyone raise your hand if you thought you've learned something that hadn't occurred to you but seemed pretty basic, because that's the... Yeah. Thank you very much. I've achieved my objective. Okay. I'll have a beer now, please, Simon.
Thanks, Gerry.
That's all right.